galaxies. The supercluster complex is a galaxy filament. Is estimated to be about 1 billion light-years long. It is one of the largest structures known in the observable universe. The observable universe is a ball-shaped region of the universe comprising all matter that can be observed from Earth or its space-based telescopes and exploratory probes at the present time. Because the electromagnetic radiation from these objects has had time to reach the solar system and Earth since the beginning of the cosmological expansion, there may be 2 trillion galaxies in the observable universe, although that number was reduced in 2021 to only several hundred billion based on data from New Horizons. Assuming the universe is isotropic, the distance to the edge of the observable universe is roughly the same in every direction. That is, the observable universe is a spherical region centered on the observer. Every location in the universe has its own observable universe, which may or may not overlap with the one centered on Earth. Beyond this limit is unknown. We don't know if there are more stars and galaxies out there, so our journey ends here. Thanks for staying until the end. Here I show you other interesting videos.
The fate of the Sun is the same as for all stars. One day, they must all eventually die and the cosmos will be plunged into eternal night.
All stars eventually will run out of fuel. The temperature of the universe drops. The stars, one by one, in the night sky will turn off. And there'll be no more new stars created. And so that the universe will end not with a bang, but with a whimper. And not in fire, but in ice.
With no fuel left to burn, a white dwarf's faint glow comes from the last residual heat from its extinguished furnace. Looking at it from where the Earth is now, it would only generate the same amount of light as the full moon on a clear night. The faint glow of white dwarfs will provide the only illumination in a dark and empty void littered with dead stars and black holes.
In some ways, it's kind of a ghost universe. It's the corpses, the zombie stars, that will take us into the future.
Asteroid belt. It consists mainly of small bodies or remnants. Welcome to this journey to the limits of the universe. I will be your virtual flight attendant. I will explain what we will see along the way. We are slowly leaving New York below. We can see almost the entire island of Manhattan. This altitude is common for commercial airlines. In a few moments we will exceed the speed of sound. At this altitude we can appreciate the curvature of the Earth. Little by little we leave the atmosphere behind and begin to witness the darkness of space. In a few moments, we will begin separation and activate the ship's engine and start accelerating. The Moon is Earth's only natural satellite. It is the fifth largest satellite in the solar system and the largest and most massive relative to its parent planet, with a diameter about 1/4 that of Earth. The Moon is a planetary mass object with a differentiated rocky body, making it a satellite planet under the geophysical definitions of the term and larger than all known dwarf planets of the solar system. The solar system is the gravitationally bound system of the Sun and the objects that orbit it. It formed 4.6 billion years ago from the gravitational collapse of a giant interstellar molecular cloud. The vast majority, 99.86%, of the system's mass is in the Sun, with most of the remaining mass contained in the planet Jupiter. The planetary system around the Sun contains 8 planets. The 4 inner system planets, Mercury, Venus, Earth and Mars, are terrestrial planets, being composed primarily of rock and metal. The 4 giant planets of the outer system are substantially larger and more massive than the terrestrials: Jupiter, Saturn, Uranus and Neptune. All 8 planets have nearly circular orbits that lie near the plane of Earth's orbit, called the ecliptic. The Kuiper Belt is a circumstellar disk in the outer solar system, extending from the orbit of Neptune at 30 astronomical units to approximately 50 from the Sun. It is similar to the asteroid belt, but is far larger, 20 times as wide and 20 to 200 times as massive. Like the asteroid belt, it consists mainly of small bodies or remnants from when the solar system formed. The Kuiper Belt is home to most of the objects that astronomers generally accept as dwarf planets: Orcus, Pluto, Haumea, Guauar, and Makemake. Some of the solar system's moons, such as Neptune's Triton and Saturn's Phoebe, may have originated in the region. The heliopause is the theoretical boundary where the sun's solar wind is stopped by the interstellar medium, where the solar wind's strength is no longer great enough to push back the stellar winds of the surrounding star. This is the boundary where the interstellar medium and solar wind pressures balance. The Oort cloud is a theoretical concept of a cloud of predominantly icy planetesimals proposed to surround the Sun at distances ranging from 2,000 to 200,000 astronomical units. These regions lie beyond the heliosphere and are in interstellar space. Alpha Centauri is a triple star system in the southern constellation of Centaurus. It consists of 3 stars, Rigil Cantoris, Alpha Centauri A, Oiliman, V, and Proxima Centauri, C. Proxima Centauri is also the closest star to the Sun at 4.2 light-years. Alpha Centauri A and V are Sun-like stars, and together they form the binary star system Alpha Centauri AB. Proxima Centauri is a small faint red dwarf. Currently, the distance between Proxima Centauri and Alpha Centauri AB is about 13,000 astronomical units, equivalent to about 430 times the radius of Neptune's orbit. The local interstellar cloud, also known as the local fluff, is an interstellar cloud roughly 30 light-years across, through which the solar system is moving. The local bubble, or local cavity, is a relative cavity in the interstellar medium of the Orion Arm in the Milky Way. It contains the closest of celestial neighbors and, among others, the local interstellar cloud, the neighboring G cloud, the Ursa Major moving group, and the Hyades. It is estimated to be at least 1,000 light-years in size. The Orion Arm is a minor spiral arm of the Milky Way galaxy that is 3,500 light-years across and approximately 10,000 light-years in length, containing the solar system. Some of the brightest stars and most famous celestial objects of the constellation, for example Betelgeuse, Rigel, the 3 stars of Orion's belt, the Orion Nebula, are within it. The Milky Way is a barred spiral galaxy estimated at 90,000 light-years. It is estimated to contain 100 to 400 billion stars and at least that number of planets. The solar system is located at a radius of about 27,000 light-years from the galactic center. The galactic center is an intense radio source known as Sagittarius A, a supermassive black hole of 4,100 million solar masses. galaxy is a barred spiral galaxy with a diameter of about 152,000 light-years, approximately 2.5 million light-years from Earth, and is the closest large galaxy to the Milky Way. The local group is the galaxy group that includes the Milky Way. The exact number of galaxies in the local group is unknown, as some are included by the Milky Way. However, at least 80 members are known, most of which are dwarf galaxies. Is the galaxy supercluster that is home to the Milky Way and approximately 100,000 other nearby galaxies. The name Longyearbyen means immense heaven in Hawaiian. The Pisces-Cebus supercluster complex is a galaxy filament, is estimated to be about 1 billion light-years long. It is one of the largest structures known in the observable universe. The observable universe is a ball-shaped region of the universe comprising all matter that can be observed from Earth or its space-based telescopes and exploratory probes at the present time, because the electromagnetic radiation from these objects has had time to reach the solar system and Earth since the beginning of the cosmological expansion. There may be 2 trillion galaxies in the observable universe, although that number was reduced in 2021 to only several hundred billion based on data from New Horizons. Assuming the universe is isotropic, the distance to the edge of the observable universe is roughly the same in every direction. That is, the observable universe is a spherical region centered on the observer. Every location in the universe has its own observable universe, which may or may not overlap with the one centered on Earth. Beyond this limit is unknown. We don't know if there are more stars and galaxies out there, so our journey ends here. Thanks for staying until the end. Here I show you other interesting videos.
From studying the dusty surface of the red planet Mars, to plunging into the hellish atmosphere of the wasteland Venus, over the last 60 years, we've launched hundreds of unmanned robotic vehicles into space, on complex trajectories to visit each of the solar system's planets, providing glimpses of our neighbouring worlds our ancestors once thought to be unattainable. But for all the fascinating discoveries and amazing achievements made along the way, humanity's journey towards the stars started out in a much darker place. A battlefront between the world's then 2 great competing superpowers. Their enduring dystopian arms race, which gripped the world for more than 40 years, was underpinned most of all by the development and deployment of weapons of mass destruction. Intercontinental nuclear-armed missiles capable of wiping out entire cities. And just when it looked like these two enemies might actually obliterate each other and bring about the end of civilization, they suddenly found a new use for their many rockets, and a new way to channel their competition.
We have vowed that we shall not see space filled with weapons of mass destruction, but with instruments of knowledge.
Всем советским людям особенно приятно, что коллективы научно-исследовательских институтов.
Consider again that dot. That's here. That's home. That's us.
A daring and dramatic goal that was not destined to be realized on this day.
1, 0.
Our story begins at the height of the Cold War, as the two great geopolitical superpowers of the time, the United States and the Union of Soviet Socialist Republics, sought to upstage one another by demonstrating technological superiority. It wasn't long before space emerged as a battleground in this standoff, initiating what has come to be known as the space race. The Soviets fired the starting gun with the launch of the first artificial satellite, Sputnik, in October 1957. And they continued to set the pace in the coming months as they launched the first living thing aboard Sputnik 2 to observe the effects of orbiting on its body in preparation for future crewed missions to outer space. Fearing that the Soviets were lurching ahead in the overall pursuit of global supremacy, the Americans kicked into life and got serious about spacefaring. In January 1958, the US launched their first satellite, Explorer 1, which discovered Earth's Van Allen radiation belt. Later that year, the US's National Advisory Committee on Aeronautics, or NACA, was dissolved and replaced with a new administration that would set their sights on the stars, the National Aeronautics and Space Administration, better known as NASA. And it was NASA who would then resume this tussle with the Soviets, repurposing old ballistic missiles into rockets as each side launched their own fleet of competing weather satellites and probes. By this time, nestling a satellite in a low Earth orbit had been mastered by both sides, and the competition soon shifted beyond the bounds of this planet to its nearest large body, the Moon. And with Earth's natural satellite now the grand prize, each side set about devising their own lunar exploration schemes. And long before the inauguration of the world-famous Apollo program, NASA established the Pioneer program, an initiative to eventually land probes on the surface of the Moon, which started out with tests to escape Earth's gravity. The first Pioneer probes were simple, carrying television scanning systems for beaming back images of the Moon's surface, microphones for detecting tiny meteorite particles in space, and magnetometers for studying Earth's magnetic field. But their first 3 attempts at launching these probes all ended in failure, allowing the Soviets to claim another milestone in the space race.
Zu einfach.
In January 1959, their Luna 1 module became the first probe to perform a flyby of the Moon, before entering into a heliocentric orbit around the Sun.
Genau wie ich es brauche.
Another 2 months would pass before the Pioneer program got off the ground with Pioneer 4, the first successful attempt by the Americans to reach escape velocity. While a guidance system failure meant it actually missed the Martian environment surrounding Earth. And with the Soviets still firmly leading the charge towards the moon, NASA broadened the battleground of the space race with the other terrestrial planets in their sights. For both starring superpowers, Venus was the obvious choice for a maiden voyage to another planet. This is because every 19 months or so, Venus's orbit aligns it with the Earth, presenting an opportune window for a relatively straightforward, minimum energy journey between the two planets. A number of these windows came and went in the early space age, with neither side quite ready to take advantage of any occurring in the 1950s. In fact, the next successful Pioneer probe, Pioneer 5, was originally intended to be a mission to Venus, but technical and developmental problems resulted in NASA missing the window occurring in 1959. As such, Pioneer 5 and each of its 4 subsequent missions thereafter would be reassigned as interplanetary space weather missions, examining solar wind, flares and ionization in the area between us and our neighbouring worlds. Meanwhile, NASA would commission a new program of more advanced probes to enable the frequent exploration of the solar system, starting with a flyby of Venus once the next launch window rolled around. Like sailors exploring uncharted seas, these would come to be known as the Mariner probes, and would make use of NASA's soon-to-be-ready deep space network of worldwide ground stations for satellite communications. But before the program could get underway, the Soviets would claim yet another win in the space race, perhaps their most seismic yet, as Yuri Gagarin became the first cosmonaut to enter orbit aboard Vostok 1 and make it back alive to tell the tale. This left the American side desperate for a win at the start of a pivotal decade for space exploration. And though their first attempt ended in failure, the subsequent launch of Mariner 2 would mark a turning point in the tussle, as the Americans would seize the initiative. Mariner 2 successfully launched from Cape Canaveral on the 27th of August 1962, embarking on a perilous voyage to Venus that was beset by technical issues and malfunctions. But despite its bumpy ride, the spacecraft made it to Venus in one piece on the 14th of December that same year, becoming the first probe to perform a flyby of another planet, and providing the US with their first big win of the space race. Mariner 2 probed the Venusian atmosphere, measured its temperature, and discovered the absence of a substantial magnetic field around the planet before drifting off into space and ceasing its operations. A follow-up Mariner mission, Mariner 5, would return to the planet some years later in 1967 to validate and reaffirm the former's findings. But in the meantime, with Venus under the Americans' belts, both sides turned their attention to another of our terrestrial neighbours, the red planet, Mars. Unlike Venus, whose surface is concealed beneath a thick, opaque layer of highly reflective clouds, Mars's surface is globally visible and relatively unobstructed. We can see its many features, faults and craters from space, rendering it a much more tantalizing target for a flyby. And like Venus, Mars also aligns with the Earth along its orbit once every 780 days, about 2 years and 2 months. And so, during the earliest convenient launch window, in November 1962, both the US and the Soviet Union launched their own maiden Mars-bound missions, with varying degrees of success. The Soviets' first attempt, known as Mars 1, launched on the 1st of November, but contact with the probe was lost shortly before arrival at its destination, and the mission ended in failure. NASA, meanwhile, made 2 attempts with their Mariner program, launching Mariner 3 and Mariner 4 a few weeks apart later on that month. While the former was lost during its launch, Mariner 4 successfully managed to escape Earth's gravity, setting out on its long journey to the Red Planet packed with sophisticated new instruments. Equipped with a camera, magnetometer and ionization chamber, as well as a cosmic ray sampler, dust detector and plasma probe, this floating laboratory survived its voyage and made its closest approach to Mars between the 14th and 15th of July 1965, coming within 10,000 kilometers of the planet. It snapped the first 24 grainy images of the surface of another world, revealing cliffs, craters, and shots of the thin Martian atmosphere. And in doing so, ironically upended the hope that we'd find Mars to be a bustling colony of life like our own. But instead of canals and reservoirs of water postulated by astronomers from the previous century, Mariner 4 revealed Mars to be a dusty, deserted wasteland, its surface evidently exposed to the harshness of space for millions of years on end. 6 years later, elapsing the Mariner 5 mission to revisit Venus in 1967, NASA prepared another pair of Mariner probes for another expedition to Mars, known as Mariner Mars 69A and 69B. Back then, NASA used to launch nearly identical probes in pairs, given the many previous failures arising from launch malfunctions that blighted their early missions. This time around, however, both probes were successful in exiting Earth and making it to Mars, following their respective launches in February and March 1969. They both performed flybys of the Red Planet in July of that same year, snapping more than 200 photos and increasing the charted portion of the Martian surface to around 20%. However, their revelations, among them the discovery of ice-filled craters in Mars's south polar region, received less than usual media coverage, having been overshadowed by a much more defining moment in the space race. A week before, astronauts Neil Armstrong and Buzz Aldrin became the first people to set foot on the surface of the Moon during the legendary Apollo 11 mission, dealing a near knockout blow to the Soviets, which left their pursuit of technological supremacy on the ropes. Having been beaten to flybys of both terrestrials and now the Moon landing, the next logical step would be to establish a more permanent presence around these two worlds. And 2 years later, in 1971, both NASA and the Soviet Union launched their own pairs of Mars probes, tasked with assembling our clearest picture of the red planet yet by not just flying past, but by orbiting the planet. NASA's first pair of Mars orbiters, then known as Mariner 71 models H and I, lifted off in separate weeks of May 1971. But only the latter, today known as Mariner 9, made it all the way. It arrived in orbit around Mars on the 14th of November, only narrowly beating the Soviet pair of orbiters, Mars 2 and Mars 3, which lifted off a few weeks after Mariner 8. All three probes then set about studying the red planet, but only one was able to overcome a major unforeseen stumbling block. Upon their arrival, all three spacecraft found the Martian surface enveloped by a worldwide dust storm, covering the planet with featureless grey clouds and preventing meaningful observations in the month that followed. But while NASA engineers were able to stow Mariner 9 in orbit until this storm had cleared, both Soviet probes immediately executed their pre-programmed tasks, using much of their available power and capacity to photograph the blank, dust-shrouded Martian landscape. It was only after this storm had cleared that Mariner 9 was then reactivated, spending some 8 months amassing a collection of more than 7,000 images, which increased the mapped portion of the Martian surface to 85%. In doing so, it uncovered a plethora of jaw-dropping new geological features missed by previous missions, including its massive Western Hemisphere volcanoes, among them Olympus Mons, by far the largest known mountain in the solar system. It also uncovered a gigantic equatorial canyon stretching for more than 4,000 kilometers across the surface, which was subsequently named the Mariner Valley. And most importantly of all, it found yet more tantalizing signs of an aquatic past on Mars. Evidence of erosion, weathering, and riverbeds from a bygone age where water once flowed on the red planet. And with such intriguing potential teased from the surface, the next step for scientists would be to get down onto the very ground, to land a probe on Mars and study it grain by grain. The Soviets would try this long before the USA. Needing to pull off something drastic to turn the tide in the space race, landing missions quickly emerged as their ace in the hole. In fact, both of their Mars orbiters that accompanied Mariner 9 were equipped with detachable landing modules, each containing the earliest recognizable Mars rovers. However, neither was successfully deployed. Shortly before reaching the red planet, Mars 2's lander was dropped on the 27th of November 1971, but its parachutes failed to open, and all further attempts to contact the probe failed as it plunged into the dusty deserts below. Mars 3's lander, on the other hand, did successfully open its parachutes and completed the first soft landing on the Martian surface on the 2nd of December. However, it only remained operational for a further 2 minutes after touchdown, not nearly enough time to release its rover. In fact, the only thing the probe was able to beam back during its brief spell on the surface was this image. To this day, astronomers are still divided over what it shows. Some claim it to be the first grainy picture of the Martian horizon, while others simply dismiss it as static and interference. In any case, the Soviets discarded the image, concluding it to be of no scientific value and writing the landers off as a failure. And each of their subsequent attempts to land on the surface of Mars ended in the same way. They would never touch down on the red planet's surface again. But somewhere they would enjoy more success in this endeavour was Venus. Having been beaten to a flyby almost a decade earlier, the Soviets spent much of the 1960s working towards a more direct approach, sending probes deep into the Venusian atmosphere. After 3 initial unsuccessful attempts as part of their Venera program, the big break came on the 18th of October 1967, when Venera 4 became the first atmospheric probe to plunge into Venus's choking toxic clouds. It returned data on Venus's temperature and chemical constituents down to an altitude of about 25 kilometers, before being crushed and melted by vice-like atmospheric pressures, some 20 times greater than on Earth. In the 3 years that followed, 3 additional Venera probes would breach the planet's cloud tops, refining its measurements down to altitudes of around 10 kilometers. And then in mid-December 1970, Venera 7 went one better, as it became the first probe to successfully land on the surface of another planet, beaming back a weak signal for around 23 minutes. Though not equipped with a camera, the probe still determined the composition of Venus's atmosphere, measured its high wind speeds, and endured its blistering surface temperature of 475 degrees. This marked a turnaround in fortunes for the Soviets right off the back of the moon landing. And throughout the 1970s, they would double down on increasingly sophisticated Venus landing missions. In 1975, Venera 9 became the second probe to touch down on the planet's surface, this time carrying a camera among its range of mounted instruments. As such, it returned the first ever panoramic pictures of the barren, lifeless Venusian ground, strewn with jagged rocky debris. And by the 1980s, Venera probes were snapping full-colour panoramas of its surface, providing our clearest window yet into this unforgiving, inhospitable landscape. The Americans, meanwhile, doubled down on Mars as a place to snap shots of otherworldly horizons, while also searching for signs of life beyond the Earth. The revelations of Mariner 9, which had teased just how water-rich Mars used to be, elevated its exploration to the summit of NASA's wish list, prompting them to pour vast sums of money into developing a series of next-generation, longer-term Mars orbiters. Carrying over successful designs from Mariner 9, they established the Viking program, constituting a pair of dual-module orbiters equipped with sophisticated landing probes that could carry out persistent research on the Martian surface. Despite a project cost of more than $1 billion all the way back in the early 70s, these twin spacecraft returned on their investments and then some, spending 6 years building up the lion's share of everything we know about the Red Planet today. Viking 1 was launched on the 20th of August 1975 and entered orbit around Mars on June the 19th of the following year. Viking 2, meanwhile, was launched a month after its twin and joined it in orbit on the 7th of August 1976. Both orbiters would spend their first month of operations scanning the Martian surface for a suitable landing site, one where the Vikings could perform biological experiments probing for signs of Martian habitability. Viking 1's lander was dropped on the 20th of July 1976 into Chryse, Planitia, where it returned the first ever clear image of the rocky Martian surface. The second lander, meanwhile, started its descent towards Utopia, Planitia on the 3rd of September. Over the next 6 and 3 years, respectively, these probes would then perform extensive analyses of the Martian soil, characterizing its rock formations and determining its geology. In the meantime, the orbiters would continue to circle the planet, acting as a relay for beaming landing data back to Earth. And throughout the duration of their missions, they uncovered troves of even more compelling evidence for a once water-rich world that played out on Mars's surface, when they saw river valleys, streams, floodplains and grooves etched into the Martian bedrock. The Red Planet was once more Earth-like than we ever could have known, with huge standing bodies of water larger than the Great Lakes. Today, however, that world has vanished, irreversibly lost to space with the sun's gradual stripping away of the Martian atmosphere. But perhaps as much as 4 billion years ago, the Red Planet may have once looked blue, and made for the earliest habitable abode for life in the young solar system. While we can't get too carried away, many of the ingredients for an awakening of life on Mars have been seen in its formerly aquatic environments. And even if only primitive, the discovery of a second source of life in the solar system would have seismic implications on our perception of the entire galaxy. If microbial life once existed on Mars as well as Earth, then it probably exists anywhere where the conditions are right. From the sealed-off, tidally heated oceans of Europa and Enceladus to the seafloors of distant Earth analogues identified by the Kepler telescope. Therefore, one of the final acts of the Viking orbiters was to scout out possible landing sites for future missions investigating Mars's habitable past. Probes capable of not just operating on the surface, but traversing it. However, the technology to execute such a feat was still over a decade off. In the meantime, NASA would turn their attention to the final unexplored terrestrial world, Mercury. Mercury represents by far the greatest challenge when it comes to flybys of the terrestrials. As the closest planet to the Sun, the solar radiation it endures is around 5 times more intense than in the space surrounding Earth. This has the effect of degrading a probe's instruments as it approaches the Sun, and presents further problems when trying to stabilize the craft to perform a flyby of Mercury. Attaining the velocity needed for a probe to reach this vicinity, moving inwards from a heliocentric orbit against the outflow of solar wind, would require an enormous amount of fuel, unless we could accrue momentum via some other means. For example, astronomers had noticed previously that when icy comets passed by a planet and felt its gravitational influence, they seemed to leave the system faster than they entered, as they were slingshotted by gravity on the way out. Applying this technique to a probe would not only circumvent the need to carry a heavy payload of fuel, but would also enable and indeed necessitate a probe to visit multiple worlds in a single swoop. As such, the 10th and retroactively final installment of the Mariner program, Mariner 10, would carry out an ambitious voyage to Mercury to study its geology and its surface features, while also swinging by Venus along the way to receive a gravitational boost. Mariner 10 launched from Cape Canaveral on the 3rd of November 1973. But unlike its predecessors, budget constraints had squeezed this mission and whittled it down from a pair of probes to a single craft designed for maximum cost efficiency, making its journey to Venus fraught by difficulties that much more worrisome for its engineers. After surviving the turbulent first leg of its journey, Mariner 10 encountered Venus on the 5th of February 1974, and imaged the planet until it departed on the 13th. During that 8-day stretch, it snapped over 4,000 pictures, including the first close-up images of the planet, a year before the Soviet Venera 9 probe touched down with a camera. It studied Venus in a variety of wavelengths, and made the first detection of its vanishingly weak, tenuous magnetic field. After carrying out its sophisticated gravitational slingshot maneuver, Mariner 10 departed Venus with a spring in its step, allowing it to press on with the most complex phase of its journey around the Sun. And in the following month, the craft executed the first of 3 Mercury flybys over the course of a year. On March the 29th, 1974, Mariner 10 flew just 700 kilometers from the planet, allowing it to compile intricate mosaics from both sides of its heavily cratered surface. It then looped back around the Sun as Mercury completed 2 orbits, before making a second flyby in late September, from a farther distance of about 50,000 kilometers, returning yet another mosaic showcasing an even greater portion of the planet. And then finally, in the following March 1975, Mariner 10 came back around for its closest flyby of Mercury, passing just 330 kilometers from the surface and snapping the most detailed set of images so far, including close-ups of its craters, maps of its various planes, and observations of its terrain in both colour and false colour. Almost immediately after, however, the probe started to malfunction irrevocably and veered away from Mercury into an unreachable heliocentric orbit. And barring the remote possibility that the craft has since impacted with a large object, it is probably still out there, circling our neighbourhood star to this day. We've been back to Mercury just the once since then, when in 2011, NASA's Messenger spacecraft arrived in orbit, carrying a much more advanced, hardy, and sophisticated range of instruments. After making a single flyby of Earth and 2 of Venus to rack up its speed, Messenger pushed onwards towards Mercury and studied it for around 4 years, snapping more than 100,000 images in just the first year of its operations. By 2013, it had mapped 100% of the planet's surface, charting its unseen side and examining its broad selection of craters. It uncovered signs of past volcanism, organic molecules, and even water ice in the planet's North Polar region, as well as shedding light on a number of the violent impacts it endured in its past. The Messenger mission concluded on the 30th of April 2015, when the probe failed to reappear on the Deep Space Network after passing behind the planet, presumably because its unstable orbit decayed until it crashed, leaving yet another scar behind on Mercury's tormented surface. With the completion of Mariner 10's mission to Mercury, each of the 4 terrestrials had now been visited and explored to some degree. And the only way we could now improve on our orbiters and landing modules would be by traversing the surface of our neighbouring worlds. As mentioned, the Soviets had tried to deploy vehicles on the surface of Mars during their failed landing missions in 1971. But it wasn't until well after the breakup of the Soviet Union 2 decades later that NASA finally honed the technology aboard their first Mars rovers. Remote-control cars carrying onboard laboratories, which could be driven across the Martian surface while being controlled from Earth. But the first successful Mars rover was a far cry from the heavy-duty research factories seen on the planet today. Sojourner, deployed from the Mars Pathfinder mission, was a low-budget attempt by NASA to test if it was even possible to operate such a vehicle. It was about the size of a microwave and ventured less than 100 meters from its landing site in Chrysi, Planitia. But over its 83 days in operation, it analyzed Martian rocks and soil and collected data on its atmosphere and climate. Its success inspired NASA to double down on a fully fledged program of advanced spacecraft and rovers, among them the Mars exploration rovers Spirit and Opportunity. They were launched in June and July 2003 and dropped on opposite sides of the Red Planet in January of the following year. Both would then venture for miles beyond their landing sites, aiming to pin down precise parameters for Mars's warm, wet past. Rover A, aka Spirit, spent 6 years roaming the Martian landscape, studying the geology and minerals in the Gusev crater for signs of chemical processes driven by contact with water. It found the rocks in the crater to be made from volcanic basalt, which did indeed show signs of interactions with small amounts of surface liquid. Rover B, on the other hand, known as Opportunity, landed in the Eagle crater of Meridiani Planum, which ultimately proved to be a more hospitable environment, with greater access to sunlight and more sheltering from Martian dust. This allowed its engineers to prolong Opportunity's operational life to almost 15 years. Covering more than 45 kilometers in that time, it extensively imaged the Martian landscape and took stunning panoramic pictures of the surface of our neighboring planet, many of which captured the eyes of the world and drew attention to the plight of NASA's rovers. And as intended, it also successfully identified signs of groundwater impacting the rocks and soil of both the Eagle and Endurance craters. Then, in 2019, after almost a decade and a half in service, Opportunity's batteries ran low and its engineers switched it off for the final time, clocking out with an emotional message to melt even the coldest of water ice. But by that time, the rover had been joined on Mars by its successor in the program, Curiosity, when in 2012, the Mars Science Laboratory touched down in the Gale crater. Armed with a drill, Among several other instruments in its extendable arm, Curiosity burrows into the Martian soil in search of the building blocks of life: carbon, hydrogen, nitrogen, and oxygen, as well as organic compounds and signs of how water may have interacted with each. Among its most eyebrow-raising findings was the revelation that the Martian soil is still around 2% water, allowing scientists to refine several key values in models of Mars's atmospheric and geological evolution. Curiosity remains active on Mars's surface as of the making of this video, 11 years since it was first switched on, and its mission has been extended indefinitely, with its robust build and clever engineering leaving no end in sight for its operations. In 2021, it was joined by the latest edition of the Mars exploration program, Mars 2020, an orbiter which delivered a similarly sized, slightly more advanced rover named Perseverance, this time with an extra trick up its sleeve. In addition to the rover, which also drills for rock samples searching for signs of past microbial life, Perseverance came equipped with another deployable vehicle, perhaps the most intuitive NASA has ever constructed. Ingenuity is a groundbreaking Mars helicopter probe that has been hailed as a Wright brothers moment in our quest to conquer the Red Planet. Upon detaching from Perseverance, it has carried out more than 60 successful flights in 2 years of operation. And its technology is a trailblazer whose successful designs are paving the way for similar future missions to the moons of gas giants. In just 60 years, we've gone from barely being able to escape Earth's gravity to operating and maneuvering on the surfaces of other worlds. The Mariner program allowed NASA to reach all 3 of our neighbouring terrestrials and set the stage for an unprecedented age of technological development and exploration. With the long road to Mars now well established, and the technique of gravitational slingshotting practiced with Venus, NASA had all the tools to press ahead with the next phase in humanity's spacefaring, travelling to the outer solar system where the giant planets lie. And around the time Mars landers were starting to materialise with the Viking program, NASA revived its old, dormant Pioneer program to undertake perhaps their greatest voyage yet, into the uncharted territory of Jupiter and Saturn. And in the next episode of this 3-part series, we will follow them out into the darkness as we embark on a journey to the gas giants. Far beyond the reaches of the 4 rocky planets, lurking on the opposite side of the asteroid belt, we find our solar system's showpiece worlds, the 2 gas giants, Jupiter and Saturn. As the 2 largest planets, both exhibit their own range of fascinating phenomena, making them tantalizing targets for probes exploring the planetary neighborhood. But with their tremendous gravitational influences, their irradiating magnetospheres, and above all, their vast distances, reaching these worlds with a probe presents a much greater challenge than travelling to one of the terrestrials. But in the early 1970s, the technology for more reliable probes capable of longer voyages was primed, and missions to both Jupiter and Saturn ensued. And it is those missions that make up the topic of our video today. In this second episode on our trilogy of probes that studied the solar system, we will re-examine their revolutionary findings over the years. From snapping breathtaking shots of their upper atmospheres to revealing seismic secrets about the moons that surround them. This is our journey to the gas giants' planets. The gas giants are the two principal planets of the solar neighborhood. Both are stunning, striking worlds with rich, extended atmospheres, each showcasing their own plethora of extreme weather processes. Any journey into their territory starts with Jupiter, the godfather planet, more than double the mass of all the other worlds combined. The clouds swirling in its upper atmosphere weave a vibrant tapestry of our solar system's oldest and largest planet. Saturn, on the other hand, is the solar system's crown jewel, with a smoother surface and an even greater number of moons, along with one of the most spectacular sights in space, its unparalleled planetary ring system. Furthermore, both of these giants host their own collections of planet-sized moons, some with eyebrow-raising prospects for habitability. As such, missions to study the gas giants have often found themselves at the top of NASA's to-do lists, with the first Jupiter-bound mission conceived as early as 1959. However, both worlds lie significantly farther from the Sun than the planets of our terrestrial neighborhood. The closer of the two, Jupiter, is around 5 times the distance separating the Sun and the Earth, while Saturn is around double that. As such, a voyage to either of these two worlds would take years instead of months, and for the planets lying beyond Saturn, whole decades would be required. It didn't seem feasible for the somewhat temperamental, short-lived probes of the late 1950s, which had barely begun to escape Earth's gravity. And so, moving into the 1960s, as NASA set their sights on the bodies of the outer solar system, the scientists at their Jet Propulsion Laboratory began investigating ways to trim down this journey time, using both clever engineering techniques and natural means. As we covered in the last episode, humanity's maiden voyages to both Venus and Mars were launched during their respective windows of closest approach, i.e., when the orbits of either planet aligned them most closely with the Earth, enabling the simplest, shortest trajectories between the two. And in 1964, a study by the JPL revealed that a similar planetary alignment event, involving all 4 of the large planets, would take place sometime in the late 1970s, the likes of which only occurred once every 177 years. This would present a once-in-a-lifetime opportunity to visit each of the giant's planets and perhaps even Pluto with a spacecraft, in only a fraction of the time required otherwise, by using each stop along the way for a gravitational boost. As we touched on last time, it had long been known by scientists that when icy comets, such as the comet Halley, passed by a planet, their velocities seemed to increase on the way out, as they received a gravitational assist upon exit. Applying this technique to a probe, specifically one flying by Jupiter, would induce a similar gravitational slingshot effect, which could effectively treble its speed and correct its course without the need to carry any extra fuel, pruning the journey time to Neptune down from around 4 decades to about 1.5. As such, the JPL quickly conceived of an ambitious series of long-distance probes that would make use of this alignment by using Jupiter as a stargate, to visit all 5 of the then contemporary planets in the outer solar system. This project would eventually materialize as the world-famous pair of Voyager probes, but that is a story for another day. In the meantime, however, NASA sought to practice this gravitational slingshot maneuver before the Voyagers arrived, while also ticking off their now most pressing planetary targets, Jupiter and Saturn. And so, in 1969, they signed off on a pair of probes as part of their Pioneer program, a dormant series of spin-stabilized probes which had some years earlier been used to study space weather. These missions, however, then designated Pioneer F and Pioneer G, would carry over old successful designs to create a new, more streamlined and resilient pair of probes fit for a much longer interplanetary voyage, one which would take them to the outer solar system. The former, today known as Pioneer 10, would become the first probe to cross the asteroid belt and reach Jupiter, before receiving a gravitational boost and ultimately shooting off into deep space. Pioneer G, on the other hand, today known as Pioneer 11, would repeat these same steps, but would then use its gravitational boost to carry on to the other gas giant planet, Saturn. Hundreds of scientific experiments were proposed for both spacecraft, and their construction was estimated to have required more than 25 million working hours. Aboard their final set of mounted instruments were helium magnetometers, plasma probes, charged particle detectors, cosmic ray telescopes, radiation detectors, asteroid and meteorite trackers, Geiger tube telescopes, and finally optical instruments for studying invisible, ultraviolet and infrared wavelengths. Pioneer 10 launched from Cape Canaveral on the 2nd of March 1972, spending about 4 months making its way towards the inner edge of the asteroid belt between Mars and Jupiter. It would enter this circumstellar fence of rocky projectiles on the 15th of July, but unlike the stuff of science fiction, its passage was smooth, barely straying within 10 million kilometers of a large object during 7 months on the inside. And save for some negligible impacts with dust particles, Pioneer 10 emerged from the asteroid belt unscathed on the 15th of February in the following year, where it started to return the first heliophysics data from the space beyond the terrestrial neighborhood. It probed the solar winds and cosmic dust for their chemical constituents, while also detecting the first helium atoms from interstellar space. After clearing the asteroid belt, Pioneer 10 maintained its outwardly passage for a further 9 months, before eventually coming within 25 million kilometers of Jupiter and initiating its observations phase on November the 6th. In the month that followed, the probe homed in on the Godfather planet and studied its surrounding environment. In doing so, it amassed the first collection of more than 500 groundbreaking images of the giant planet and its great red spot, before making its closest approach on the 3rd of December. But as the craft crossed Jupiter's magnetic equator, it was exposed to a huge electron flux, some 10,000 times stronger than the most corrosive surrounding Earth. This wreaked havoc on the probe's instruments by generating a series of erroneous commands, which threatened to derail the mission altogether. While its engineers were able to rectify most of the troubling issues, only 6 of the spacecraft's 11 core instruments remained operational as they were turned back to image Jupiter's moons. As a result, an image of the moon Io, as well as some close-ups of Jupiter itself, were lost. And while the craft was able to capture 2 of the other Jovian moons, Europa and Ganymede, only images of the latter yielded any meaningful detail. Upon starting its exit from the Jupiter system on December the 4th, Pioneer 10 became the first probe to receive a gravitational assist from another planet. catapulting the craft en route towards its final destination, interstellar space. Having accrued so much velocity from its trajectory through the Jupiter system, Pioneer 10 had now been set on an irreversible path, becoming the first man-made object to reach the solar system's escape velocity, i.e., the speed needed to overcome the gravity of the Sun for the duration of the journey beyond. Covering more than 500 million kilometers a year, Pioneer 10 crossed the orbit of Saturn just 3 years later, in 1976, followed by the orbit of Uranus in 1979, and then Neptune in 1983. It would continue along this path for another 15 years almost, before its vanishingly weak signal became too faint to transmit any readable data. But while the mission was officially concluded on the 31st of March 1997, Pioneer 10 would continue to beam back the occasional featureless telemetry signal for a further 6 years. In fact, the very last contact with the probe was on the 23rd of January 2003, from a distance of more than 80 astronomical units, finally capping off what was originally intended as a 21-month mission after more than 30 years. A true testament to the craft's engineering and the time that was invested in future-proofing its design. Just over a year after the launch of Pioneer 10, the subsequent follow-up mission, then known as Pioneer G, was prepared to follow. Like the former, this spacecraft would float across the asteroid belt en route to the Jupiter system, before passing the large planet to receive a gravitational boost. But unlike its predecessor, which was slingshotted straight into deep space, Pioneer 11 would carry on towards the other gas giant, becoming the first probe to visit the solar system's crown jewel. There, it would study its atmosphere, magnetosphere, and its planetary rings, as well as the many intriguing moons in orbit around the giant. And upon completion of those pre-programmed objectives, Pioneer 11 would be used to test a slingshot maneuver of its own, flying through Saturn's ring plane. The probe lifted off from Cape Canaveral on the 5th of April 1973, embarking on an 18-month voyage to Jupiter through the asteroid belt. It encountered the giant planet in early November 1974 and made its closest approach a month later on the 2nd of December. It came within just 43,000 kilometers of Jupiter's cloud tops, 3 times closer than its counterpart the year before. But it did so at a much higher velocity, resulting in less prolonged exposure to damaging radiation. As such, all of the craft's 11 instruments this time survived their encounter, snapping over 200 even sharper images of the planet, including the first shots of its polar region and more of its swirly outer atmosphere. The probe also enjoyed more success in studying the Galilean moons, snapping shots of Io and making measurements of Callisto where Pioneer 10 was unable. Upon receiving its bespoke gravitational boost, Pioneer 11 would venture onwards for another 5 years before encountering its next target, Saturn. On the 29th of August 1979, Pioneer 11 entered the Saturn system and spent 3 days sinking towards the planet en route to its closest approach, just 21,000 kilometers from its outer edge, snapping increasingly close-up images all the while. It then became the first probe to cross Saturn's ring plane, as a dry run for the Voyager spacecraft, which were already en route to the gas giant. In order to receive the kind of gravitational boost from Saturn required to push further out into the solar system, it is necessary to fly close enough to the planet that the extended ring plane of particles must be breached. Therefore, Pioneer 11 would practice flying through a gap in Saturn's rings in order to map a sufficiently clear route for the voyagers. And if it had sustained any serious damage upon colliding with unseen moonlets, Voyager 2's ice giant's mission to Uranus and Neptune would probably have been scrapped. But Pioneer 11 glided through smoothly with no problems, and received a gravitational assist from Saturn that sent it hurtling onwards on the interstellar phase of its journey. The Pioneer probes maintain their outward passages to this day, both now over 100 astronomical units from Earth, verging on the very periphery of the Sun's extended atmosphere. And their journeys will continue for millions of years to come, first entering interstellar space, and then eventually passing by other stars in the Taurus and Scutum constellations. One can only guess at what or who these probes might encounter given enough time. Perhaps the Pioneers will pass by planets hosting intelligent life. And though both probes are now defunct, we did make alternative arrangements for this optimistic eventuality. Attached to both spacecraft is a postcard from humanity to anything that might find them in the distant future. The Pioneer plaques were designed by Carl Sagan and his peers. They are gold-finished aluminium slabs inscribed with general information about humanity, including a depiction of the human body overlaid on the probe for scale. It also depicts the order of the solar system and features a pulsar map for triangulating the position of our planet, using neutron star emissions for reference. However, each one of these symbols has been criticized for being much too anthropocentric, not to mention the fact that the pulsar map is now obsolete. But if nothing else, these plaques and their accompanying probes are unmistakably engineered. And if intelligent life does exist around other stars, as Sagan predicted, then perhaps they may one day see these probes streaking across their skies. Imagine if we found something like this coursing around the solar system. The repercussions on society, culture, and politics would be unprecedented. With both gas giants reached by the dawn of the 1980s, the next step would be to return to these worlds with more persistent probes, capable of not just flying past, but orbiting the gas giants. In the decade just gone, Mars orbiter probes had gone from science fiction to reality, most notably through Mariner 9, a groundbreakingly successful mission to study the red planet for more than 8 months through 1972. Therefore, when work began on a Jupiter-orbiting probe later that decade, successful designs from the Mariner program would be carried over. But by the time this spacecraft had materialized almost a decade later, its administrators felt that its technology had evolved sufficiently beyond its Mariner bases, warranting its own mission classification, and was thus reassigned as the Galileo spacecraft, named in honor of the discoverer of the 4 large Jovian moons, Galileo Galilei. This probe consisted of both an orbiter and a detachable module that would be dropped into Jupiter's upper atmosphere. However, the technology to both develop and test this Galileo entry probe would not become available until during the 1980s, and other unforeseen factors also hampered and delayed the Galileo mission. Everything from bad weather, test failures, lawsuits targeting the probe's nuclear technology, and even the Challenger disaster led to its launch being delayed all the way through until 1989. But at last, the probe did finally lift off from Earth on the 18th of October, aboard the Space Shuttle Atlantis, which delivered it to a low Earth orbit. It would then execute a series of engine burns and thrusts to guide it into a heliocentric orbit, where it would receive both slingshots and course corrections from flybys of the Earth and Venus. After accruing enough momentum, the probe then embarked on a long, arcing trajectory through the asteroid belt, before coming within range of the Jupiter system in mid-July 1995. Almost immediately, the Galileo entry probe was released, and slowly drifted towards the cloud tops alongside its orbiter. It would take another 5 months before the entry probe finally breached Jupiter's atmosphere on the 7th of December, travelling at around 50 kilometers per second on impact. It then spent around an hour sinking beneath the cloud's edge, plunging to a depth of more than 180 kilometers, hardly scratching the surface in the grand scheme of the giant structure, but still returning invaluable insights on the increasingly hellish conditions unfolding below. It measured chaotic wind speeds of more than 600 kilometers per hour, with temperatures climbing to a scorching 16,000 Kelvin before the probe's heat shield finally succumbed. Back in space, and the orbiter prepared to fire its engines to decelerate and achieve orbital insertion, making it the first probe to be captured by a world in the outer solar system on the 8th of December. Over the next 7 years and 9 months, it would take no less than 35 long laps around the Jupiter system, spending only short periods of time up close with the planet to give its instruments time to recover from exposure to radiation. Over the course of its mission, it assembled an extensive, comprehensive dataset for the Godfather planet and its surrounding environment, making astounding discoveries on both counts. It captured an active volcanic eruption on the torrid moon of Io, and on closer inspection, revealed lava flows on its surface for the first time. It also mapped Ganymede's surface in much greater detail, identifying complex magnetic field activity around this almost Mars-sized moon. And on Europa, it uncovered the strongest evidence yet for a long-speculated ocean of liquid water, atop which the moon's icy crust is thought to be suspended. Upon exhausting its fuel reserves, in September 2003, the Galileo spacecraft's engines were fired for the last time, as the probe was intentionally steered into Jupiter, in order to avoid crashing on one of the moons and contaminating a potential subsurface ocean. It then followed its entry probe to a crushing demise and concluded its mission on the 21st night of September 2003. But as one door slammed shut, another swung open, because the end of the Galileo mission to Jupiter coincided with the start of the first Saturn orbiting mission by the spacecraft Cassini-Huygens. Cassini-Huygens is one of the flagship missions of the 21st century. Like Galileo, the spacecraft consisted of an orbiter accompanied by a detachable probe, but not an atmospheric probe this time around. Rather, a landing module for plunging into the thick, dense clouds that shroud the surface of Titan, Saturn's largest moon. This mission was conceived in the early 1980s, only shortly after the success of Pioneer 11, as the US's National Academy of Sciences formed a coalition with European partners eyeing future collaborative missions. A Saturn orbiter to study both the gas giant and its principal moon quickly emerged as the general consensus, but its development was stunted by financial disagreements and squabbles on the American side. Eventually, however, both NASA, the European Space Agency, and the Italian Space Agency agreed to the project, and the mission was designated Cassini-Huygens, after two prominent 17th century European astronomers who made seminal contributions to the study of the gas giant. Giovanni Cassini was an Italian astronomer who studied Saturn and its surroundings, and was the first to identify gaps in its ring structure. Christian Huygens, on the other hand, was the first to correctly conclude that these rings are not part of the planet itself, while also spotting the moon of Titan in 1655. And like its namesake astronomers, the Cassini-Huygens spacecraft would perform extensive analyses of Saturn, its rings and its moons, targeting more than 20 distinct objects during the primary phase of its mission. During this time, it would release its landing module, the Huygens probe, which would descend upon Titan's frozen surface, giving us our first look under the hood at this fascinating, complex atmospheric oddity. After around a decade in development, Cassini-Huygens lifted off from Cape Canaveral on the 15th of October 1997, setting out on a 7-year voyage towards the solar system's crown jewel. After entering a heliocentric orbit, the craft gathered pace with 2 flybys of Venus in the 2 years that followed. This gave it the kick it required to embark on its long voyage to Saturn, calling it Jupiter along the way for a gravitational boost. It encountered the Godfather planet in December of the year 2000, and after spending 6 months in the Jovian system, it snapped over 26,000 stunning images, among them the iconic shots of the Galilean moons eclipsing the clouds of their host. After receiving its gravitational slingshot, the probe pressed onwards towards Saturn for another 3.5 years, all the while beaming radio signals towards the Sun to test the curvature of space-time and the predictions of general relativity. It then started its approach towards Saturn in June 2004, executing the first in a series of complex, risky maneuvers. In order to achieve orbital insertion, the craft had to roll back on itself and fire its engines along its path to decelerate until it was captured in orbit by Saturn. This required briefly misaligning Cassini's antennae with the Earth, but the craft came through the maneuver flawlessly nonetheless, and reconnected to the Deep Space Network to commence with its 4-year primary mission. First up on the agenda were flybys of a number of Saturn's smaller icy moons. It passed by Phoebe on the 11th of June 2004 and studied its bright patches to infer the existence of water ice. Soon after, the moons Methone, Pallene and Polydeuces were identified lurking in early Cassini images of the system. But the spacecraft was soon focused on its principal satellite target, Titan, the unique planet-like moon with a dense atmosphere, unlike anything else in the solar system. As such, Titan has always been viewed as an essential component of missions to Saturn, with Cassini carrying out no less than 45 flybys of the moon during its initial 4 years of operation. The first came in October 2004, when it passed just 1,200 kilometers from the tip of Titan's clouds. Its infrared and ultraviolet instruments then began peeling back the layers of this atmosphere for the first time, compiling preliminary maps of Titan's surface with a view to identifying a suitable landing site for the Huygens probe. And on Christmas Day 2004, Cassini's gift to Titan was sent hurtling down towards its clouds, finally penetrating their outer edge about 3 weeks later. It recorded and relayed its 2.5-hour descent, beaming back around 350 images of the approach, though a further 350 were lost in a software failure. But on the 14th of January 2005, the Huygens probe landed in Titan's Adiri region and continued to broadcast what it saw for a further 90 minutes. In that time, it captured the first and still only glimpse we have from the surface of a body in the outer solar system. These images show boulders of reflective water ice, frozen as hard as rock by Titan's brutal surface temperature of minus 180 degrees. But what makes these images particularly interesting is that these boulders appear to have been smoothed by another flowing liquid, though certainly not water at this low temperature. Rather, Titan is home to a network of lakes and rivers of liquid methane, which Cassini found indisputable evidence for in 2006. In fact, Titan has a methane cycle which bears striking resemblance to the water cycle on Earth. And if we were to warm Titan up, this methane would evaporate, and the water ice mountain ranges would melt to take its place. Thus, in the very distant future, when the sun has swollen to red giant stature and the Earth has been swallowed whole, it is Titan that may have the best hope for a future awakening of life, with rivers, streams, weather and precipitation to mix up its surface-dwelling abundances of organic compounds. Another of Saturn's moons with intriguing prospects for habitability is Enceladus, though it bears a quite different set of potentially life-giving characteristics. Enceladus is smaller than Titan and lacks a substantial atmosphere for supporting life on its frozen surface. But like Jupiter's moon Europa, Enceladus is thought to have a buried subsurface oceanic layer, which is warmed and tidally heated by gravitational resonances in the Saturn system. These motions cause friction within the moon's interior, resulting in energetic upwellings in the liquid layer, which press against the icy surface and refreeze, creating faults and sometimes even causing cryovolcanic eruptions. In 2005, around 2 months after the Huygens probe had touched down on Titan, Cassini saw the outline of an ice geyser eruption at Enceladus's south pole, as it spurted out plumes which regularly fall into orbit along Saturn's ring plane and replenish its frozen material. A few years later, and Cassini went one better, as it flew straight through one of these water-rich plumes during a flyby of Enceladus, sampling its chemical constituents and all but confirming the presence of a tidally heated, salty liquid ocean beneath its surface. With so much exciting potential seemingly locked away within these moons, it's easy to lose sight of Cassini's other studies, including its extensive analyses of Saturn's rings. Using radio signals and occultation, it determined their 3D structure, dynamics and consistency by identifying both fine structures and more complex gravitationally bound clumps clearing gaps in the ring's material. The probe also studied a number of extreme weather events playing out in Saturn's upper atmosphere, starting in 2006 when a cyclone was seen near one of its poles. It also studied one of the planet's most jaw-dropping features, its iconic North Pole hexagon, another enormous eyed storm extending almost 30,000 kilometers, which was originally found by the Voyager spacecraft. Between 2008 and 2017, Cassini observed gradual color changes in this cloud pattern in response to seasonal changes in its exposure to sunlight. And then, in 2010, it saw something visible only once every 30 years, Saturn's Great White Spot. This storm bears resemblance to Jupiter's Great Red Spot, but unlike the latter, it did not persist for very long or stay rooted in one place. Instead, it whipped around the face of the planet, leaving long trails of suspect white discharge in its wake, which slowly faded away over a number of years. By this time, Cassini had completed the primary phase of its mission which lasted 4 years up to July 2008. But with plenty more fuel in the tank and its battery power still well conserved, its engineers were able to extend Cassini's operational life by an additional 2 years. This enabled the probe to study Saturn during its equinox events in 2009, thus coining the mission extension's title.